Hi, my name is Stephen and today I'm joined by Jack, Tom and Zacc. Together we will explain our project, the Graphene Biosensor Reader. The Graphene Biosensor Reader is a research tool that allows a wire-bonded graphene field effect transistor, or GFET, configured as a biosensor to be inserted and analysed, producing tabulated results of the electrical properties of the transistor and biomarker, which can be viewed by the user. The reader is particularly useful within the medical industry, where biomarkers can be placed upon the sensor and then analysed by converting its properties to an electrical signal. This electrical signal can be analysed and referenced to pre-existing data through the use of correlation curves, allowing the researcher to determine the concentration of a particular analyte to provide a confident diagnosis of an existing medical condition. The final specification of this system will be discussed throughout this presentation, but first let me pass you over to Zacc, who will explain the reasoning behind the choice of this project.
When deciding on a project to undertake, we as a team had several different ideas that had to be considered from various sources. It wasn't until our nanotechnology module, specifically the part discussing 2 and 4 probe measurements on graphene, conducted by Dr. Shakil Awan, that allowed us to consider this project as an idea. Throughout the module, 2 and 4 probe tests were conducted on graphene and graphene FETs, and from this, a niche was found. Firstly, from seeing how the tests were conducted using expensive multi-purpose equipment that required a long setup time. And secondly, seeing the potential improvements that this technology could have on the future of detection and diagnosis of disease. The GFETs were fabricated by Dr. Awan's PhD student, Carrie Haslam, as shown in the picture. Carrie optimised the functionalisation protocols to enable highly sensitive detection of a number of protein biomarkers, as a proof of concept technology for single sensor based detection. To date, the biomarkers that have been functionalised consist of clusterin for Alzheimer's disease, HCG for cancer biomarkers, and troponin I for cardiovascular diseases. Our project has extended the single sensor technology to enable multiplex detection of multiple biomarkers simultaneously. This has the potential to significantly improve the confidence level of disease diagnosis at a much earlier stage than it is possible compared to the current state-of-the-art clinical tests or evaluations. By use of the biosensor reader, the need for expensive multipurpose equipment is no longer required, and by using wire-bonded sensors, the speed of conducting tests is severely reduced, meaning research into further disease diagnosis can be completed at a much faster rate. I will now pass you on to Steve, who will explain the hardware designs and how they have been implemented within the system.
In order for the system to conduct the tests, as carried out by the research team, the 2 and 4 probe measurements method is implemented. In order to achieve this, circuit designs were developed so that a minimal amount of components were required and that the components used had little to no effect on the overall results of the system, such as voltage loss or additional resistances, and where they do have an effect, that they are compensated for within the software elements of the system. This system starts with a current limiting circuit to ensure that a maximum current of 10 mA is provided. This means that the device under test will be protected and not receive an overcurrent that could damage it. A 5V supply powers the system, and an accurate voltage in the millivolt range is achieved using an array of potential dividers, wired together in such a way that they divide the source voltage into tenths, hundredths and thousandths of a volt. In order to get this voltage as accurate as possible, digital potentiometers are used that have 100 steps each. These are then wired together to allow 10 mV to be divided over 100 steps, ensuring a 1 mV step can be achieved to be as accurate as 0.1 mV. Buffers are then used so that the resistances of the sensors do not alter the supplied voltage. As a requirement of the research conducted, a voltage range of -100 mV to +100 mV is required. The potential divider array allows for a range of 0 volts up to 1 volt in steps of 1 mV, and this is then reversed by the use of 2 single pole double throw switches. These switches connect to the input power on one pole and ground on the other, with the other switch having these poles reversed, creating a circuit when the switches are in the same position. The common pin connects to the device under test so that from the device's perspective, when both switches are in their first position, the power has a positive polarity. Then when the switches are switched, the device sees the power as negative polarity, meaning the switches work together to form a basic H-bridge. One more digital switch is used, which allows for the different GFETs to be selected. To allow for testing of multiple channels, multiplexers have been implemented as a means for channel selection and filters added to reduce any noise that may have been picked up from the device through the multiplexers. Buffers then allow for a differential amplifier to compare the voltage received from the channel multiplexers before being passed into an 18-bit analog to digital converter, providing an accurate as possible measurement of the channel. Finally, a current sensor resistor of 1 ohm is used, and this voltage amplified so that microamps of current can be detected. Combine this with the voltage from the resistor array and the voltage from the channel, and the 2 and 4 probe measurement of the device can be conducted with a 99% accuracy rating. The component choice and design creates a standardized system that, as the research is improved and refined, mean minimal changes are required to the hardware to compensate for the amount of sensors or the variation of sensors used. All of this circuitry is controlled by a microcontroller unit that has been coded using the C coding language, which I will now allow Tom to explain.
The software for controlling the hardware and for processing the captured data into a readable and usable format for a user is written in the C and C++ coding language, utilising embed operating system and libraries. To design each aspect of the code, the data sheets for the selected components were combined with flowcharts to create the individual functions to either operate the hardware or process the analog to digital converters captured data into an understandable format for the users. To allow for an efficient code, multiple processes are coded into different threads, so when a process has been undertaken, rather than the system sitting in the waiting state, other tasks can be conducted, such as aligning the multiplexers to the correct channels, acquiring data through the analog to digital converters, and setting the voltages for the next set of channel testing. To ensure a voltage is supplied for the test, an algorithm has been implemented that checks the voltage supplied from the variable resistors potential divider array, adjusting it up and down until each voltage value passed into the test is as close as it can be to the 1 mV required steps. The voltage is then passed through each of the sensors and different channels on the sensor selected one by one. This is repeated for each sensor and for each channel automatically and as per the definition supplied by the user when the test is configured. With accurate defining of the voltage steps and automated testing of each channel, the test can be carried out and the results captured accurately using 18-bit analog to digital converters. The captured results from the analog to digital converters are further averaged within the code to ensure that the results captured are as close to the actual values as they can be, therefore providing an accurate and confident result from the test conducted. The final step of the processing of the data was to allow the saving of information to an SD card. The data collected from the test will be saved into a tabulated CSV file that the user can convert and graphically represent in such programs such as Origins. This saved file could be read directly from a computer application via Bluetooth or through removal of the SD card. The computer-designed application allowed for the selection of tests, which sensor and channels to conduct the request tests on, and for the specific test details to be configured. Zacc will explain further on the design and functionality of the computer application.
The bespoke computer application has been designed utilising extensible application markup language and C# coding, using Visual Studio to design and simulate both the appearance and functionality. The purpose of this application is to allow the user of the system to control the biosensor reader. There are multiple tests that can be selected, including a defect test, which is essentially the 2-probe measurement test, utilised to gain an indication of the working functionality of the sensor, and the 4-probe test, used for obtaining accurate measurements for each device. From the application, the user can set which tests they wish to include within their research programme. If the defect test is to be conducted, the resistive limit can be set by the user. Any sensor with channel resistance greater than this value will not be included when further and more accurate tests are conducted. If the 4-probe test is also to be conducted, it can be configured through defining the voltage range and voltage steps that are desired to be captured for this test. After selecting the required tests, the application will display a layout of the biosensor. On this layout diagram, the the type of devices inserted into the reader can be selected from either asymmetrical, symmetrical, or a mix of devices before the specific channels are chosen. With all the selections entered and submitted, all this data can be passed through to the microcontroller unit wirelessly through Bluetooth, where the software then ensures that the correct tests are conducted and channels monitored. This data is stored and saved to the correct CSV file for the sensor used, each with its own unique file name. The stored CSV files are sent via the same Bluetooth connection from the microcontroller unit back to the PC application and can be viewed via Excel on the host PC, saved to a desired location. This data can then be accessed and utilised by the research team as required. The computer application completes the build of the system by allowing the user to control and access the data from the 2 and 4 probe tests. But to get to this stage, testing was conducted at each opportunity to ensure a complete and functional system, the specifics of which Zacc will now explain.
Testing has defined the project's parameters and settings and helped to shape the project's design. To start with, Proteus was used to design the individual parts of the project, such as current limiting, voltage stepping, and channel selection circuits. By using Proteus, each design could be simulated individually in order to understand how the components worked, and then piece together to simulate how each component would interact with each other. Through these simulations, component choices were made for the hardware, understanding what amplifications were required, noticing where the voltage drops occurred, and understanding which components added additional resistance to the overall circuit. Due to the nature of 2-probe testing, any additional resistances needed to be considered, so finding this information out early meant that it could be accounted for and components selected to reduce this impact. With simulations completed for the system, a testing specification was designed for each individual component and for the integration of the components, working its way to a test specification for the final system. The test sheets provided a critical analysis of each section of the design and allowed for the testing and the build to be carried out in order to further support each simulation, providing an actual value of losses and accuracy rather than a generic and simulated response. Although time-consuming, by carrying out thorough testing and the recording of the results on the test sheets, the multiplexer's resistance was found and confirmed that each channel contained the same resistance, which due to the multiplexer's positioning in the 4-probe test meant this resistance is negated. The 18-bit ADCs were tested and shown that the impact of the noise had made a large difference to such an accurate device, and that the voltage drop of the H-bridge was far too large when passing millivolts through, and therefore analog switches were used to provide the same outcome as the H-bridge. The thorough testing provided a huge amount of detail to the workings and the operation of the design, and the weaknesses that could be amended in the future to improve the quality of the system.
The system built can conduct 2 and 4 probe measurements. This provides the basic information relating to the detection of certain conditions by analysing biomarkers placed upon the sensor. The next stages of developing this system would be the ability to conduct a backgate test and an alternating current test. The backgate test would provide valuable insights into the leakage of the device and how the biomarkers affect its leakage. The backgate test provides a large voltage to the backgate of the GFET and a constant current across the source and drain. The backgate voltage is then swept through the range of -100 volts to +100 volts. The AC tests and 4-terminal pair work in a similar method to the 4-probe test, but rather than stepping through a voltage range, we'll step through a frequency range, noting how the impedance changes as different frequencies depending on the biomarkers placed on the sensor. Similar to the backgate test, the results provide further information on the analysis of the biomarker, but rather than analysing the voltage differences the biomarker causes, the AC test determines the impedance properties of the biomarker. Once all tests have been implemented, the next logical step is to introduce a comparison algorithm that compares all the data collected from previous tests and tests conducted using known concentrations and known biomarker samples, in order to provide the most accurate of diagnosis conditions. When the confidence of the test results can be assured and enough testing completed to provide a database of results to compare against. This device can be marketed for the medical industry, allowing GPs, doctors and nurses to take a sample such as blood and drop it into the sensor so that any medical condition can be efficiently and accurately diagnosed.
Throughout the design and build of this project, several challenges have been encountered and overcome. These challenges provide insight into the parts of the project that the team consider to be the most proud of. With the project revolving around a product that is currently in its research phase, the project itself was subject to change. The GFET itself has been developed and designed enough to be produced in mass, and this allowed the next step, which involved wire bonding the sensors to a chip. The wire bonding process has provided us with significant hurdles to overcome, starting out with a design that incorporated multiple sensors that would require 120 pins, and this reducing down to 5 sensors that could be wire bonded to a 48-pin chip holder, and then a final wire bonded design of 2 sensors on a 28-pin chip. By designing a standardized system, the changes made to the final chip design meant that minimal changes occurred to the hardware, from the first iteration of 120 pins required to the final iteration of 28 pins required. This also works in reverse, as where the sensor is developed and more devices bonded to a chip, then the minimal changes to hardware need to be made as the system has considered and been designed for this occurrence. Another issue that was overcome came in the form of completing such a large task from our separate homes. Completing a task in such a manner meant several issues occurred, mainly in the form of limited resources. Being in the university environment and surrounded by knowledgeable people, such as lecturers and technicians, can provide help and insight, as and when required. But by being removed from this environment, several of these issues had to be overcome on our own, or delayed until members of staff were available. Due to limited access to the university and the labs, when it came to the build of the project, considerations had to be made when components required surface mounting. This was counteracted by using JLC and creating our circuit designs on EasyEDA. Using JLC and EasyEDA meant that there was no need to solder, allowing a considerable amount of the system to be created whilst working from home. This meant an increased use of the budget and additional lead times due to outsourcing the build, but less dependability on the university's resources and equipment. Although not everything in the project was completed, as explained in the future improvements for the project, to get as far as we have done with the time and resources available is a defining moment for the project team, and to be able to have an impact and lay the groundwork down for such an innovative design is something we are all proud of, and hope that the future of this project can have the impact on the medical sector that was foreseen from the start of the project. Thank you.